So in this last problem, we have one more example of a way that a related rates problem that you might find on the AP test could be tricky. So the first one we had with the cone, tricky in the sense that when you took the derivative, when you found dv dt, you had to notice you had two variables and stop and use the product rule. So taking that derivative was where the hard work came in. And the last question, the police chasing the speeders, the tricky part there, I would bet so much money that the most common error on that problem was not recognizing that your dy dt was negative. So making sure we have a picture, making sure that even though you have the numbers in the picture, numbers that go with the problem, recognizing when you have a distance that's decreasing, making sure that you use a rate of change that is negative. This last one, I think, here you'll have to write your own equation to relate the variables that you're interested in. And this is the one where the equation is least obvious, I think. So here we go. We have a hot air balloon. This is from your textbook. They tell us, not that you would necessarily know what this means, but so there's a balloon that's going to launch straight up. And 500 feet away from the launch point, we have what's called a viewfinder. So there's somebody, you could pretend there's an eye right here on the ground, and it's tracking the angle between the ground and the balloon. So see this angle, which happens to be labeled theta in the picture? That angle is changing. You could imagine if we tried to draw this picture with a higher height for the balloon, that angle would have to be bigger. So here's what we know so far. We know that the rate of change of that angle with respect to time is 0.14 radians per minute. And we've been asked, how fast is the balloon rising? So some things we know this distance across here is 500 feet. The height of the balloon is changing, and the angle that the balloon makes with the ground is changing. But we know the rate at which that angle is changing. So how fast is the balloon rising? Again, the first thing we want to try to figure out is what variable, what quantity, what rate are we looking for? So how fast is the balloon rising? That has to do with how fast is this distance between the ground and the balloon changing. And you can see in this picture, so this picture came with the problem, so that's nice. You might find that for the AP test in a related rates problem, the picture might be drawn. The thing we're looking for is dh dt. We know d theta dt. In fact, they even labeled it d theta dt for us. So that's going to help set us up. We have this picture. We know that we need dh dt, and we know d theta dt. So we're going to need to write an equation that relates not the two derivatives we know, but the variables implied by those derivatives. So is there any equation that we could write that includes only the information that we can see in this picture and the variable h and the variable theta? So I think there is. We can, so it's a harken back to your trigonometry days, your geometry days, whichever you want to think of them as. This angle theta is changing. We know something about the side opposite, and we know something about the side adjacent. So the tangent of theta is the opposite over the adjacent. That's going to give us the relationship that we need in this problem. So tangent of theta is opposite over adjacent. Don't get confused with h for hypotenuse, because we've labeled h to mean height in this problem, and it's the side opposite theta. So I know that tangent of theta is going to equal h over 500. Once I have that equation, and I can take the derivative of both sides with respect to time, then I can use whatever other sneaky methods I need to, like, plug in numbers or freeze the picture, but this is what I want to know. So the derivative with respect to time of tangent theta is the derivative with respect to theta of tangent theta, which is secant squared of theta, times d theta dt. That's implicit differentiation. And here, the other side, that's h divided by 500. The fastest way to take that derivative is to think of that as 1/500th of h. Then it's just 1/500 times dh dt. So I was really hoping he wouldn't wake up so early. So we're going to finish the video very quietly in a different room. Okay, so the derivative of 1/500th times h is 1/500th times dh dt. Now I can freeze this picture. What can I use in place of theta? Well, I've been asked a question about the time when theta is exactly equal to pi over 4. I'm going to replace theta with pi over 4. Do I know dh dt? No. Do I know d theta dt? Yes. So I'm going to be able to replace theta. I'm going to be able to replace d theta dt. I'm going to be able to isolate dh dt. This is great. At this point, you can even multiply both sides by 500, and you've isolated dh dt. If it's a free response section, you could be done. But if we need to simplify, even in the free response section, we're going to have to be able to figure out what secant of pi over 4 is. So if whatever you do, if you draw the unit circle, if you want to make a triangle, whatever you can do to figure out the secant of pi over 4, they're all fine, whatever method you have. But here's one way. Okay, so some of my other stuff is in the way. So here's a triangle, a right triangle, an isosceles right triangle because I have an angle of pi over 4. So if I know these two sides are the same, 1 and 1, the hypotenuse is radical 2, and the secant is 1 over the cosine, and cosine is the adjacent over hypotenuse, 1 over radical 2. So it's going to be 1 over radical 2, radical 2. So once you can write this expression, we're just simplifying dh dt. You can find that's 140 feet per minute.